thank you for the introduction, and also I want to thank the organizers for the chance to speak here. So the talk is on Trojan-horse attacks on CVQKD systems. And this is the laser pointer. This was a collaboration between the Max Planck Institute for the Science of Light in Erlangen and SecureNet from here, and also Telekom Paris Tech. And so let me just give you an introduction to hacking and Trojan-horse attacks. So quantum hacking, as you've seen already in how can I go back? This one? This one? Oh, no, it doesn't work. No, this goes forward. Oh, no, yeah, now it works. Okay. Okay, as was already shown by Renato Renner, if you do a security proof, you need some assumptions to make that work. And but if you look at the publications, you will see that we have some successful attacks on these QKD systems already. And as such, there is a discrepancy between the claim of unconditional security and the actual practical implementations that exhibit loopholes, as shown before. So what we want to do with quantum hacking is strengthen practical QKD systems in the end. So just to illustrate that again, you have a theoretical model on one side, and you have some assumptions, and some of those may just be incorrect or insufficient to correspond to the actual implementation. Or the implementation may have technological deficiencies or imperfections, as Shihan has just shown. So in the end, this may allow Eve to obtain a portion of the secret key without getting detected. So let me just illustrate the Trojan-horse principle again. What you start out with is this prepare and measure type system. You have Alice, you have a laser and a modulator, and you have a quantum channel and Bob as the receiver. And usually the modulator imprints the quantum states on the light pulses emitted by the laser. So just for illustration, this is a binary protocol for coherent states. And now what Eve's objective is to read out the state of that modulator without disturbing the original quantum system. So she also has a laser and a receiver, and she uses the source of back reflection as a tool to read out the modulator. So what she does is she prepares that Trojan-horse pulse and sends it into the system. The intensity of the pulse decreases, and it picks up the modulation and gets analyzed by Eve's receiver. However, if you do this kind of attack, you should think about some things for it to be successful, namely when to send in the pulses or expect the back reflections to return. So you need to know where the source of the back reflection is, because you have to time it to the modulator. The next thing is, how many photons do you want to send? So you need a loss information of your components inside Alice, and also what color to choose, so what wavelength, because the system might behave differently for different wavelengths. Then, of course, Eve has to think about her receiver, like which is the best way to detect the actual modulation here. And in the end, she doesn't want to be discovered by Alice and Bob, so she has to find a way to circumvent the detection mechanisms by Alice and Bob. So just to illustrate some sources of back reflections that you might use. If you have an open connector, this will give you a reflectance of minus 14 dB. So this is like a normal fiber patch cord with a flat end. And if you look, for example, at an angled connector, it has a reflectance of minus 45 dB already. Or a laser surface, which could have any value, but that's what we measured for the laser we tested in the system. And you can also have some other options, like a closed APC connector, which also gives you a reflectance of minus 60 dB. Or even inside this electro-optic modulator, you will have some optics, and these optics have surfaces, and all those surfaces will act as a source of reflections. So in the end, Eve can use different surfaces of the components inside Alice for her attack. So Eve wants to stay concealed while doing this, but what plays against Eve? And as already said before, you have some mechanisms of monitoring, and of course you have your actual detectors that you need for your QKD system. So from those detection statistics, you can make your security proof, and of course, you expect some detection rate or some parameter from your system, and if that deviates from what you expect, then maybe Alice and Bob can say that Eve was present or not. And also, of course, from the QBER, that shouldn't cross the abortion threshold. The other thing you can do is have actual hardware countermeasures. So as Shihan showed, the watchdog detector, or you can install isolators or optical fuses or wavelength filters, but more about that later. So I want to show you the experimental setups. We performed this attack on two setups. One is the SecureNet system, and one is our home-built CVQKD system. Just so you understand what this system is outputting, you have a train of pulses where the train alternates between local oscillator and signal pulse. And as such, as I told you before, the Erlang system just outputs a binary modulation, so that's encoded in the signal here. And the pulses are orthogonally polarized. The SecureNet system does the same thing, only that it uses Gaussian modulation in the signal states here. So they are both time and polarization multiplexed, and Alice actually prepares a local oscillator, so there's no real local oscillator in Bob. So let me just highlight the differences of the two systems. You have a laser in the beginning always, and then you split up into a local oscillator and a signal path. Similarly here for the SecureNet system, local oscillator and signal path. And one of the main differences between the two systems is this one is all in single mode fibers, and this one is all in polarization maintaining fibers. As such, there are polarization controllers to make the pulses orthogonal, whereas here this is done via a Faraday modulator. Faraday mirror. And the position of the delay line to produce this train of pulses is different. Here it is before the amplitude modulator, and here is after the modulators. Also, as I told you, the Erlang system produces a binary modulation, so you just modulate along one quadrature axis, whereas this one has access to the whole phase space using amplitude and phase modulator. Also, another component that is subtle but could be critical to such an attack is the way the fibers are connected. So these vertical lines here correspond to flat surfaces of connectors which have a higher back reflectivity, whereas these angled surfaces have a lower back reflectivity. So this one, these connectors would be harder to use as a source of back reflections. So in order to answer the questions that I've posed before, you need to know when the pulses, when to send in the pulses into the system and what photon numbers to use. So in order to analyze that, we used the technique of optical time domain reflectometry. This works like that. You have a device, this OTDR device. It has a laser. It sends in some pulses and analyzes the back reflection, like the timing of the reflection and the amplitude. So what you usually have is a device like this, and you see a trace that looks like this. And for example, this part here would just correspond to the fiber scattering in here. And this could be an open connector, like the reflection of an open connector, which is very high. And after the open connector, we have just air, and therefore the back reflected light drops into the noise floor. So that's what we did on the SecureNet system, also on our home build, but I just show you results for the SecureNet system. We connected the OTDR system to the SecureNet system and connected the components one by one, so we get a feeling for when the back reflections occur and what amplitude they have. And you see that the open connector always has a big reflection, but you see also that inside these components may also be some other reflections. So you see a coupler and another PBS. And then the system continues here, so this is just a continuation of the whole plot with a different scale because of the delay line. And you see that the Faraday mirror has a huge reflection, and in the end what you want to read out as Eve is of course the phase modulator and the amplitude modulator. So that's where you want a reflection to occur. So your pulse travels inside here, gets reflected, and you pick up the modulation of amplitude and phase modulator. So from those measurements, we derive possible attack paths. So the light enters into Alice. We craft the polarization such that it takes this path here, gets reflected, and goes over here to the amplitude modulator, where it has only suffered 14 dB of losses. And now you get a lot of losses because of the reflection inside the amplitude modulator, but that actually allows you to pick up the phase of the phase modulator So the light travels back and travels back out, and overall you get a reflection or a loss of minus 75 dB, which is still quite challenging. Similar to this, you can also take another path, so the light also travels through this here and gets reflected off this laser surface. The advantage here is that you read out both modulators and not only one as in this scheme here. So it gets reflected here, and in the end you have a loss of 84 dB. So that's what you have to deal with when you want to hack this system. So I'll show you how Eve is constructed. Eve also has her laser to inject those Trojan-horse pulses into the system, and in the end she wants to do homodyne detection on those Trojan-horse pulses to find out the phase information and the amplitude information. So she also has a local oscillator, and she just prepares those two pulses, lets the local oscillator wait in the system while the other pulse picks up the phase modulation. They interfere here and get detected by this double homodyne detection. So this is the actual hacking setup. It's outside, so we have set up a live demo here. So we brought the system here and connected it to a SecureNet system. You will see it at the industry exhibition, and yeah, we show it whenever possible. So this is what a typical trace looks like. These are unwanted back reflections because, as I told you, there are many different reflections, but not all might have the phase or amplitude information. So the pulses we're interested in are these ones, and you maybe also see it already. You just put a discrimination threshold here, and you can see that this corresponds to plus alpha and minus alpha. So these are the back reflected homodyne signals. Now here are our measurement results for our Erlangen system. We inject the light into the system and look for the signature of this binary modulation. And as you can see from this measured data here, from this Q function plot, you can just draw a line here, and you see already that it's a very high success probability of greater than 98%. The same thing we did for the SecureNet system, where you can also see that they have quite a huge gap between them, so you could discriminate them easily. But the SecureNet system actually uses Gaussian modulation, not binary modulation. We did the binary modulation only as a first test to see whether the attack works. I have to say this data is a little bit preliminary, so I don't have any numbers for you yet, but it will at least show some plots illustrating this. So what you want to do is, what Alice wants to do is prepare a Gaussian modulation. So she has to prepare a specific kind of amplitude modulator distribution and a uniform phase modulator distribution. And as such, you can plot those two distributions against each other in like a phase space diagram. And what we pick up from Eve's homodyne detection when performing the attack is something that looks like this. So if you just plot again the quadrature amplitude and the quadrature phase, then you can see that these distributions correspond to each other, and also the phase looks roughly uniform. But my colleague said to me this data is not convincing, so we looked for different phases here in this plot and checked whether the phases actually correspond to the quadrature phase space. So as you can see, this red phase here, for example, corresponds to this one, and adjacent to it should be the green phase here, which you can see here, and also the colors continue around that. So it's just flipped and rotated. So at least the phase works, but we still have to make some calculations on what the success rate really is. Now let me give you a picture of the loss analysis. So we take this path here, this round trip path with the 84 dB losses, and analyze what we've done in this graph here. So you have the complete round trip loss plotted here against the photon number you need to get at least one single photon back. So for example, for a 60 dB loss, you need 10 to the 6 photons to get one single photon back that you can analyze. So when this connector here is closed, so when the laser is connected like a normal operation of the SecureNet system, you have 84 dB losses as shown here. However, to make it easier, because we only have limited laser power and it's hard to find the right lasers for higher powers, we have opened this connector, and as such the requirements are a bit less, and we need only like minus 54 dB of losses, and therefore only less photons to perform the actual attack. So this is the data I've shown you before. Now we wanted to make this a little bit more realistic and increase the attenuation of this variable attenuator here, and set it to 20 dB. And as you can see from the measurement data, you can still discriminate the two states from each other. However, in a realistic attack, the connector here would be closed and not open, and also the attenuator would probably be set to something like 30 dB. So we would be up here, which is already almost 10 to the 12 photons, which is a lot. So we wondered how is it with fiber damage. And if you just go to the design wavelengths of 1550 nanometers, you see that the connectors limit the damage, and you get a power of 1 watt roughly before your fibers break. So if you plot that power here, then you see that for the actual case, the attack wouldn't work. So what can Eve do to make the attack still work? She has to use multiple back reflections, and that's what I've shown you before by showing the two paths that are possible. And I'm sure there are other back reflections that could be used or simultaneously homodyned. So in the end, I want to talk about what's the impact on, for example, MDI systems, so measurement device independent QKD. And as you know, measurement device independence is given on the detection stage, but not on the source stage. So in this protocol, you have this Charlie Bell test set up here, and you have Alice and Bob producing the actual states. But Alice and Bob still use a modulator to encode their states. So in that sense, Eve could still do the same attack. And for that, I want to show you one proof of principle implementation of this. You can just forget that here because it's the same as Bob. And you can see that the polarization, or this modulator here, corresponds to the amplitude modulator in this actual implementation. So when Eve wants to hack that, she just has to connect herself here, inject the light here. It would get reflected somewhere at the laser surface, and you can get it back. Of course, again, it's a numbers game, so one would have to try it, but in principle, this attack would work on MDI systems too. So what countermeasures can you perform? We had this before with the watchdog detector and possible countermeasures, but you can also talk about an isolator or a wavelength filter or maybe even optical fuse that blows when there's too much power inserted. So I want you to look at that graph here below. This is from a publication we recently made, like a risk analysis on these Trojan-horse attacks. And you see that the design wavelength for 3 different isolators is 1550 nanometers. So here they have a huge round trip loss. So when the light passes in the wrong direction through the isolator and then the right direction. But at other wavelengths, for example, like 1300 nanometers, you can see that the Trojan-horse pulse would only suffer a 20 dB attenuation. And that's not much. So in the end, you have to analyze whether you could do the same attack with 1300 nanometer light and still succeed. So you have to be careful choosing the right isolator or choosing the right watchdog detector or a combination of those to cover the right spectral range and efficiencies. So that's it. These were the people responsible for this work. So my colleagues Nitin and Birgit are here in the audience too. And this is my group leader, Christoph Marquardt, my professor, Gerd Leux, and the people from SecureNet, Paul and Sebastian, and of course you all know Eleni. So thank you for your attention.
So you analyzed like pre-parameter schemes.
Yep.
How does it look like if you have a kind of like entanglement-based scheme, like a squeeze state? I mean, in Alice's lab, she produces, and then she's doing the measurement.
I think it all depends on whether you have an active component or a passive component. So we thought a little bit about this, on what kind of systems this would work. And if you just imagine a source that has no active component like a modulator, then of course you cannot perform a Trojan-horse attack on it. But I mean, in the end, you have to think how your light would propagate into Alice or into some sender, and whether it would be able to pick up a signature of whatever process is used to generate the light. Yeah.
Thank you.
You said the power is limited by the laser damage threshold.
Yep.
Did you actually have any components failing?
No, the power was not that much. I mean, our laser was in CW, I think it's a maximum of like 10 milliwatts or 50 milliwatts or something. That's why we actually relaxed the power, the power requirement by tuning the attenuator or leaving a connector open. So that's what we wanted to present with the loss analysis, to see where you could go with this and whether it's still feasible with high powers. And maybe one interesting aspect of this is if you have high powers, for example, if you insert 1 watt into the system, and you think that your fiber damage threshold is slightly above that, then you would still be able to do so. But then you think about it again, and maybe your modulator has a lower threshold. So 1 watt would destroy the modulator, but in the end, the light has to get through to the modulator first. So you might be able to use 1 watt as an input power, and until it gets to the modulator, it might have the right power in order not to destroy the modulator. So it gives you some room to play with as Eve.
So I guess another countermeasure that you could try would be to restrict the back reflections coming from the system. Did you
to restrict them?
that? Or try to reduce the back reflections?
Yeah, sure. I mean, I've shown this slide before where we saw different components that have different reflectivities. So if you just compare the Erlang system to the SecureNet system, I've told you that the Erlang system has all flat connectors and the SecureNet system has angled connectors. So even that reduces already the chance of back reflections. What you could also do is splice systems, so splice fibers together. Or for example, if you have a modulator, you could use anti-reflection coatings. So in the end, all of these measures would come together to reduce the chance of a successful attack.
Just let me follow up on that. So what is the dominant reflection in the experiments that you've done? Are they from the connectors?
Yeah, the dominant reflection we used was from the connector. There was, maybe I can show you from the, maybe just go back. So here, these were the two attack scenarios, and so we ran these OTDR tests on the systems and put again all numbers together, and from this we made a simulation of all possible attack paths using these sources of reflections, and these were the two highest possible reflections. So one was the one here, the PC connector in front of the laser, and the other one was within the amplitude modulator.
When you insert your Trojan-horse light, did you increase the axis noise? Have you measured the axis noise?
You mean of the actual QKD protocol?
Yes.
No, this was done as a proof of principle attack, so the Alice was not connected to Bob. So
Okay.
if you wanted to do that, then if Alice was connected to Bob and you insert Eve in the middle, you would have to use a fast switch to allow the normal quantum states to propagate from Alice to Bob and inject your own states in the time slots where they don't disturb the actual light.